Hi guys. So today I want to talk about types of reactions. And as a reminder, RxNS is my shorthand for reactions. So when you see that, it just means reactions. So the first type of reaction that we talk about in class is a synthesis or a combination reaction. And what happens in a synthesis reaction is that you have two or more substances that react together in order to create one final compound. So you can see that the generalized formula here is A reacting with B to produce compound AB. Now you can have more than two substances that come together. The important piece is that they come together and only produce one product, because that is what makes it a synthesis reaction. So a real-world example would be the formation of water. So I have hydrogen gas, H2, reacting with oxygen gas to produce the water molecule. So I have two things that are combining together to create one product, and that's how I know that it's a synthesis reaction. Now the opposite of a synthesis reaction is a decomposition reaction. So with decomposition, you can see that I have the generalized formula here. AB, so compound AB, breaks down into its parts, A and B. Now just like with a synthesis reaction, I could have more than two parts that this breaks down into, but as long as I have my one compound breaking down into multiple pieces, that is what makes a decomposition reaction. So for a real-world example, we can look at the decomposition of hydrogen peroxide. So H2O2 solution, this AQ means aqueous, it means it's a solution. Okay. So hydrogen peroxide solution decomposes into water and oxygen gas. So I have my one compound breaking down into multiple pieces. So that's decomposition. Single replacement is our next one. And with single replacement, you have an element that reacts with a compound to produce a new compound and a different element. Now it's called single replacement because, as you can kind of see here, what happens is that I get a swap. So element A comes into the compound and actually creates your new compound with C. And that is how we end up with compound AC as a product. And B, the original element within the compound, gets kicked out, and you can see that B ends up on its own in the product. So we have one swap. A comes in to make the new compound, and B gets kicked out and is on its own. So a real-world example of this would be if I had iron reacting with copper 2 sulfate solution. And you can see what happens is that I end up with iron 2 sulfate and copper. So iron, just like in the generalized formula, came in and created that new compound with sulfate. So I have iron 2 sulfate solution now. And copper ended up getting kicked out of that compound and ends up on its own as a product. Now the interesting thing with single replacement is that it will only happen like this if your elemental metal is more reactive than the metal from the compound. And to determine if it's more reactive, we use what's called the activity series of metals. So this is the activity series of metals, and it goes from most reactive at the top down to least reactive at the bottom. So lithium is at the top, most reactive, and silver is at the bottom, least reactive. Now you'll also notice that hydrogen is in the list, even though it is not a metal, but hydrogen participates in single replacement reactions and is able to take the place of copper, mercury, and silver, and so it is included in the list. Now, in order to take the place, like I said, you have to be more reactive, meaning you have to be above whatever metal you're trying to replace in the activity series. So if I look back at my example, iron and copper, okay, iron is here, okay, and copper is down here. So you can see that iron is above copper, and therefore iron is more reactive than copper, and that is why it is able to take its place. And this reaction actually proceeds, and you get these products. Okay? For an example where this would not happen, if I was trying to get zinc to take the place of sodium within a compound, well, zinc is lower than sodium in the activity series, meaning that zinc is less reactive than sodium, and therefore it is not able to take the place of sodium. So if I tried that, I could wait as long as I wanted to, but nothing would happen. I actually wouldn't have a reaction there. So it would just stay products. Nothing would happen. So in order for a single replacement reaction to take place, you need to have your element, the thing that's trying to take the place in the compound, higher up on the activity series than the other. Just like iron was higher up than copper, and so I actually get that reaction to run. Double replacement is very similar to single replacement, except now I have two swaps. Okay? So you can see the generalized formula here is compound AB reacts with compound CD to produce compound AD and compound CB. Now another difference between single and double replacement is that with double replacement you can see that I've got two compounds that react together, whereas in single replacement I have an element reacting with a compound. So that's a first clue that they're different. The second clue that double replacement reactions are different is that normally both of these compounds are going to be aqueous state, meaning both of these tend to be in solution when we have double replacement reactions. Now for the double swap that I was talking about, you probably see it already, but A comes in and swaps with C, and that is how we get compound AD as a product. And then C also swaps in and creates a new compound with B, and that's how we ended up with CB. So you can see the two swaps to get two new compounds. That's double replacement. So an example of this would be silver nitrate solution, AgNO3, aqueous, reacting with sodium chloride solution, so NaCl aqueous. And you can see that I end up getting silver chloride, which is a solid, and sodium nitrate, which is aqueous as well, so it is another solution. So just like in the generalized formula, what happened was that silver swapped over and created that new compound with chlorine, okay, and sodium swapped over and created that new compound with nitrate. So I had my double swap and I ended up with two new compounds, and that is double replacement. The last type of reaction that we cover is complete combustion, specifically the complete combustion of hydrocarbons. Now a hydrocarbon is any compound that only has carbon and hydrogen. So this would be the generalized formula of a hydrocarbon, where X and Y represent any subscripts that you can think of. Okay? So with a complete combustion, we have a hydrocarbon reacting with oxygen gas, and then we make the products of combustion, carbon dioxide gas and water. Okay? So a real example of that would be the combustion of methane. So methane, CH4, reacting with oxygen to produce carbon dioxide and water. Now there are other ways that you can have a combustion reaction, but we don't cover them as often in this class or as in depth in this class. But even they follow that oxygen is a reactant. So if you're looking at a combustion reaction, you're always going to notice oxygen gas as a reactant. And for our class specifically, it's always going to follow this format where you have a hydrocarbon reacting with oxygen to produce carbon dioxide and water. And those are the 5 types of reactions.